So, okay. Has the recording started?
Yes.
Okay. So today we are going to talk about the weak LP space, very basic conception in harmonic analysis. The whole content is covered in GTM 249, which in my opinion is a very good textbook for us to study the harmonic analysis. So we start with the distribution function. So f be a mu measurable function. Mu is just a normal measure in a subset of Rn. Then the distribution function of f is defined as the function as the measure of the level set. So very simple, huh? Okay, now we have a few properties of these distribution functions. For example, the monotone monotone property, the scalar property, the similar as some triangle inequality. And all of these, I could say that these properties are all trivial from the definition, and indeed they are, but still I like to prove the second and the third property that because they will be applicable in the last section of this lecture. Also, I believe this is a wonderful opportunity for you guys to get used to this definition of this distribution function. Yeah. So for the second one, very natural, we write the definition for the left-hand side with a C here. And because C is non-zero, so we divide the C into another side. And this is coincidentally the distribution function. Okay, so that's for the second one. And third one is a little bit more difficult. Let's try to write out the definition for the left-hand side would be some measure of the level set, and the right-hand side, measure of the level set, measure of the level set. After some observation, it is natural for us to conjecture that some kind of inclusion holds. Yeah, and this is true indeed because of triangle inequality. So we rewrite our proof from this inclusion because of the triangle inequality, and then we take complement on both sides. We get this set is a subset of this union, and then we take measure on both sides, finally obtain the desired result. Yeah, this is not hard. And for the first and fourth properties, I'll leave them as an exercise, okay? It's not hard, trust me. Okay, this is the distribution function. Next, we introduce a beautiful application of the distribution function. In harmonic analysis, also other fields of analysis such as PDE, operator theory, anything related to analysis, we are always handling the LP norm. So it would be desirable for us to obtain an alternative representation of LP norm. And here is one of them. So suppose X mu is a sigma finite measure space. Then for F in LP, and there P is not only between 1 and infinity. Now we can enlarge the area of P to 0 to infinity. We have this beautiful representation formula for LP norm. Okay, the proof is not hard again. We write the definition of this distribution function, And very naturally, we exchange the integration. And because alpha in this, the domain of alpha can be restricted because of this from 0 to the absolute value of fx. So we obtain this one. And finally, after easy computation of the integration, finally you obtain the pth power of the LP norm. Yeah, not very hard. And for those of you who are familiar with all-Lich spaces, you would know that LP space is only a special case for all-Lich space. So we could also expect some similar identities holds for all-Lich norm or all-Lich integration. Actually, we have something, yeah. I forgot this one. Okay, just this remark. We have this if phi is a continuously differentiable function, with we can assume that phi is a Orich function. Then we have a similar representation formula for this. Okay. Okay, so let's get back to this question. Where was sigma finite applied in the proof? Let's see this proof. We emphasize that X mu should be a sigma finite measure space, but where did we apply this condition? Does anybody notice that? Um, do you know what is a sigma finite measure space? Okay, maybe it's too, I mean, too old, not very familiar concept for everybody. Is in the measure theory. Now the sigma finite condition is applied to when we exchange the integration, because the Fubini theorem ask us that the measure should be satisfy the sigma finite condition. Is there any question about this? Okay, nobody answered. Okay, now it's ready for us to define the weak LP space. So P between 0 and infinity, we define the weak LP space as the set of functions, mu measurable functions, satisfying the superior of this one less than infinity. And we define this superior as the weak LP norm. Okay, so gamma, then the distribution function 1 over p, then take the superior. This is the one. Okay, the reason we use the notation LP comma infinity to denote weak LP space is that there's yet another larger or generalized space called Lorentz space, which is denoted as LP comma Q, and we can prove that this weak LP space is a particular case of that Lorentz space when Q equal to infinity. So for the simplicity of the notation, we use LP comma infinity to denote the weak LP space. Okay, so firstly, let's have a look of the relationship between our weak LP space and our traditional LP space. We have the very beautiful embedding. If a function f is in the traditional LP space, then it is in the weak LP space, and with this inequality. So we have the embedding, the traditional LP space is subsetting the weak LP space. So the proof is very traditional. We write the left-hand side out because the left-hand side is a superior. Remember, the superior of gamma, then the distribution function 1 over p. So we take the pth power of the left side, then is alpha to the power of p, then the distribution function. By the definition of the distribution function, we write the definition out, insert this alpha to the power of p to the inside, and then use the very famous Chebyshev's argument. We replace this alpha by the absolute value of fx, because here in the domain, alpha is less than the absolute value of fx. Then we enlarge the area of integration to the whole space, and this is the pth power of LP norm. Then we take pth root on both sides. Then we take superior alpha positive. We obtain the desired result. Any question? Okay, of course, the inclusion is strict. For example, we can have a function fx defined as this in one dimension. Then we compute its classical LP norm. This improper integral is divergent. But when we compute the weak LP norm, alpha to the power of p distribution, then after a few computation, it is finite. So we find an example, find a function that is not in the classical LP space, but in the weak LP space. So the inclusion is strict. Okay, so finally we have a look at the structure of the weak LP space. We are going to prove that the weak LP space is LP, infinity, quasi-normed complete linear space. It is, in fact, we have said many times the weak LP norm, but indeed it is not a norm. Because the triangle inequality fails, as you can see, maybe 5 minutes later. But all of the other properties holds. And the LP infinity space equipped with this, let's say this is a norm, is complete. This is kind of a strong conclusion, in my opinion. Okay, according to the definition, we have to check a few several properties. As starters, we will prove that the norm-relevant properties, as what we did in traditional LP space, we consider two functions in weak LP spaces to be equal if they are equal mu almost everywhere. Okay, so under this assumption, the weak LP norm is 0. By definition, is equivalent to the superior is 0. The superior is 0 is equivalent to, for all gamma positive, this is 0. And it is not hard to say that this means the distribution function is 0. Then we can deduce that the f is 0 mu almost everywhere. And for the second one, because the distribution function has this scalar property, we can very easily to deduce that this weak LP norm has this scalar property. And finally, for the triangle inequality, As I told you, triangle inequality in
What
fact
what is
fails.
K here?
K is any any complex number.
But it's the same as C
Yeah. Actually, I could have used C. Yeah. Okay, thank you. And for the triangle inequality, as I told you, the triangle inequality in fact is a failure. But we have a compromised one by taking this distribution property as alpha beta equals to alpha over 2, then we can have multiply this alpha to the power of p on both sides. We have this inequality, and it is very natural for us to give it 2 power of p in order to make this one is a LP, weak LP norm, right? Okay, so there's a 2 to the power of p left out. Then it is less than or equal to 2 power of p, this norm and this norm, because the norm is defined as a superior, okay? Then we take pth root on both sides. So the left side and take the superior over alpha non-positive. Then the left side becomes this weak LP norm, and the left side becomes this. We apply this elementary inequality, which will be left as the second exercise. And then we obtain some constant here, which cannot be eliminated. And then this F and G's weak LP norms. So the triangle inequality fails, but with a not very large constant here. Okay.
Can I ask a question?
Okay, no problem.
Uh, this looks a little bit like proving the inequality for the Orlich functionals, right? So
Yeah.
can one use this weak LP quasi norms to define a norm with a strict constant one and the triangle inequality? Or?
This is a very good question.
Maybe it's
Uh,
not convenient for some other reason, but
yeah, as far as I know, there's no such kind of improvement as you suggested. So I would say that this might be some difficulty inside.
but is it possible that a weak LP norm has all the properties like Orlich functional?
Uh,
He is probably satisfied, yeah.
Maybe, yeah, yeah. For the moment, I don't know, but I think it's good to explore. And from the books and materials I read about Orich norms and weak LP norms, they rarely connect these two things together. So maybe something we could explore, okay?
Okay, so, but
Mm-hmm.
then, of course, this kind of inequalities are interesting.
Mm-hmm.
In fact, you get a lot of this kind of almost Minkowski inequalities when you study
Mm-hmm.
homogeneous norms on nilpotent Lie groups.
Yeah,
They are usually coming with some constant. Yeah.
yeah.
Okay.
Okay, thanks for your remark. Okay, so now it remains to show the completeness, okay? In classical LP theory, we have multiple strategies, multiple approaches to argue the completeness of the classical LP spaces. One of the way to do that is through the conception convergency measure, which is very useful here to do analogies argument for weak LP space. So we have a brief review of the convergency measure. We have a series of function fn and a function f, but all of them are measurable functions. Then fnx is said to be convergent in measure to f. For all epsilon positive, there's an integer n0 such that for all n greater than n0, this measure is less than epsilon. I think all of you are familiar with this conception. There is an analogous one, quotient in measure. We just simply replace this fx by some fmx and write the quotient statement out. And then this right as a definition of the quotient in measure. Yeah.
The epsilons are the same.
Yeah, we could take the same epsilon and we could also take the different epsilon. There's a delta and then epsilon. They are actually equivalent.
Yeah,
Yeah.
that is nice. Okay, I never
Yeah.
seen it.
Yeah. They are equivalent in fact. Okay. Okay, so in traditional LP space, we use the following approach. Because we want to prove the completeness, so we firstly begin with extracting a quotient sequence in LP. Then we argue quotient sequence in LP implies quotient in measure. Then we use the raise theorem to say there is a subsequence that convergent almost everywhere. And then we use some maybe Lebesgue dominated theorem and also the Fato's lemma, something like that. Finally, to deduce that this accumulated F we have found is actually Fn minus this F in LP is also convergent to 0. This is what we did in the classical LP space. And now we only have to, change the classical LP space to weak LP space and go with the analogous approach. And the only thing left for us is to deduce that quotient in weak LP space implies quotient in measure. And this is indeed not very hard. Let's have a look at this proof. We assume Fn is a quotient in the weak LP space. Then by definition of the quotient and also the norm of LP infinity, we have for all epsilon positive, there's an integer n. For all n m greater than this large n, we have this superior is less than, here we take epsilon to be this. So here we apply the alternative definition as Professor Zagaliski has suggested. We take different epsilon delta here, right? You could prove that these two definitions are indeed equivalent. So there's no difficulty of that. Okay, so we obtain the superior is less than epsilon to a weird power. And then because the superior is less than or equal to this, so everything is less than or equal to this. So we take alpha to be epsilon and divide this alpha epsilon to the other side. This is coincidentally the definition of the quotient in measure. So that's it. Yeah, we can now from quotient in weak LP space, then to the quotient in measure, and then we follows the traditional way and argue the completeness of the weak LP space. So that's it. Yeah. Okay, any question? Yeah, finally, there are a few exercises for you. In my opinion, doing exercises is essential in math study. So the first one is, as I said, the properties left for the distribution function, which in my opinion, will help you to get used to the distribution function. And the second one is the inequality, the traditional inequality. This type of inequality, this kind of, I name them as P inequality. There are a series of these P inequality are very useful in doing estimate, especially in harmonic analysis, also in PDE and other fields. So it is very good if we could collect some of them. And finally is interpolation, um, interpolation property. We know that if F is in LP, in LQ, then F is in LR for R between P and Q in classical LP space. I think all of you know how to prove it, but we'd like to review it. And then what can you conclude if we exchange this traditional LP by our weak LP space? What can you conclude? Yeah, this could be a spoiler for the next lecture. Okay. Okay, so that's it. Any question? A very short lecture.
So what will you tell us about applications?
What application? You mean weak LP space?
That's right.
Yeah, that's for the next lecture. We got this very beautiful interpolation property.
Excellent.
Yeah, yeah.
Okay.
That is way better than this one. Okay, this is uh, just a starter.
Okay. Would be that too much work to ask you to say few words about Lorentz spaces?
Oh, there's in fact, yes, but there's
Maybe these definitions or some basic properties. Or...
okay. Now,
But you told us about the special case, right? So, uh, and
yeah, in fact, then we because now it's hard for me to write any formula. How could
no,
I?
no. Next time, no, there's no.
Okay, okay, okay. I understand. I understand. Okay, I'll
Okay,
try that. Okay,
excellent.
okay. So how could I how could I finish this?
Sir, do you want to go back or
No, no, no. Just
okay?
close everything. Oh, there. Okay, okay, okay. Okay. So Wang Chun
Yeah.
would stop recording.
Yeah. Thank you.